Okay, so yeah, let's begin. Um, Hi, so my name is Niket, and I'm a PhD scholar at IIT Bombay, and I'm going to be taking the live sessions for this course, Introduction to Statistical Mechanics. Uh, so something about this course, it's an 8-week course. Uh, as you know, you some of you might have taken more NPTEL courses previously. Every week there will be a set of lectures released. You have to go through the lectures. It's important that before you attend these sessions, you have gone through those lectures and you have seen the problems at least. I It might be not always possible to solve the problems before you come for this, but at least you should have glanced through through the problems to know what kind of problems are there, so that these sessions will be more effective for you guys. Um, Another piece of advice about this course is that I think in one of the lectures even professor has mentioned that it gets technical very fast. So it starts with it starts as initial two lectures are some basic theory. You can see that he's giving some historical context, some basic permutation combinations. So you might think that this will go steady, but then start right from the third lecture, it hits a very different note. It becomes very technical. So it is very important that you keep on solving with pen and paper yourself. All the derivations that sir has done in the classroom, you might think that you understood it well, but trust me on this, even if you think you've understood well, do derive it yourself without seeing what sir has done. Otherwise, if you're taking an exam for this course, it will be very hard to follow later on. Initially, 1 2 weeks you might be able to follow, then you will have to give up the course. I'm not saying it's a very tough course. What I'm saying is you have to keep on working along with the course. Oth- it's a very informative, it's a good course. You'll understand statistical mechanics quite well, but uh, don't be lazy in solving the problems. That's all I'm saying. Okay, so I think we can start with. Okay, so in these sessions, basically what I am going to do is I'm not going to exactly, so the teaching part is already done by the professor. We'll solve some sample problems, and sample problems generally, what we do as teaching assistants, we take previous year problems and we solve them for you. So you get an idea, you get a hang of how to solve the problems that are in the current week. And once you get a hang, you can solve the current week problems yourself. We don't actually go and solve the current week problems. All right. So that's what the strategy is going to be even in this, even in my case, that I'll be solving the previous year problems. Say for week one, previous year problems I'll be solving today, in the next 2 hours. And subsequently, you have to get an idea from these lectures and solve it by yourself. Also, there will be a recording of these sessions. I'll be posting a recording link. So those will be like what I am doing here. There will be a YouTube link for that. So if you are not able to come for these sessions, you can watch it on YouTube later also. But it's preferable that you attend live sessions because that's the whole point. Like already you are watching recorded lectures of the professor. There is no live interaction with the professor except a couple of sessions that will happen during the semester. So if at all there are some doubts, you can right away get cleared in these sessions. Otherwise, if it's just my thing, I will be teaching only those problems. I'll be solving only those problems, explaining only those problems. But if you have some doubts, you can directly ask me in the live session. If you are not clear with any of the lectures, any particular derivation, if you have any such doubt, I will be helping you as much as I can. If at all I'm not able to help you right away, I will go through it. I'll ask the professor and I'll get back to you. So any doubt that you have in the lecture, there are two ways. You can directly ask me in the live session or you can post it on the forum. Please use the forum, guys. I have seen that generally people who take the course don't use the forum. So please use the NPTEL forum, post the questions there. The professor will be answering there and I also will be answering there. So please post the questions on the forum and you can ask me in the live session as well. All right. Yes. So let's begin. I'll directly start. If you have, okay, so let me begin with this. Do you have any doubts in the three lectures that you've watched in this week? So because this is a live session, I will require some response from you guys. Yes, no, can't say, whatever. Some response is very much essential because otherwise it seems like I'm just talking to walls. So, uh, someone, whoever can unmute their mics, just say yes, no, whatever. I'm not even sure whether I'm audible or not, whether I whatever I've said. Please, someone unmute and say. Maybe I'll take names now. Um, who are there in the meeting? Yeah, Varathan. Varathan, please unmute and tell me whether you have any doubts in the three lectures that have happened this week. Varathan, good evening. Do you have any doubts in the lectures? You don't have a doubt. Have you watched the lectures or not? What's the problem? I'm speaking very fast. Okay, okay. Okay, okay, okay. Sure, will do. Yeah. Okay. So, if at all anyone has any doubt in the lectures that have happened, the three lectures you can ask right now. You can post it in the forum, whatever works for you guys. Um okay, so just let's start with the previous year assignment questions. I have not seen the assignment this year. Uh, so, whatever the questions are, honestly, I don't know whether they are repeated or not. Okay, so this is your first question. Um, the first question is the entropy of an isolated system always dash and becomes a dash at the state of equilibrium. So, what do you think is the answer for this? Someone will have to give me an answer. This is a very simple multiple choice question. Does not require solving. This is just conceptual. So, so what you're trying to say is the entropy of an isolated system always increases and becomes a maximum at the state of equilibrium. Does everyone agree, or is there someone who disagrees with this answer? Okay, so that's the correct answer. For an isolated system, so they have specified that it's an isolated system. So for an isolated system, the entropy always increases. Okay, and it becomes a maximum at the state of equilibrium. That is what we've learned. What about a system which is not isolated? For example, you have a system which is exchanging some heat, or there is some work being performed externally on some system. What do you think? The entropy of that system which is not isolated, even that increases or it can decrease? Here we are talking about an isolated system. What I'm trying to ask is the entropy of a system which is not isolated, which is actually exchanging heat and matter and things with the environment. What happens with the entropy of that system? Mahesh Raghavan, tell me the answer to this. I can see Mahesh in the meeting. Mahesh, tell me the answer to this. Good evening. Decreases and maximum. For this question or the one I asked? The entropy of a system which is not isolated. Actually, just a moment, there are people joining. Okay, so for for a system which is not isolated, the entropy does not necessarily increase or decrease. So think about it. You can have a system which is losing heat to the environment. You can have a system like, for example, there are systems which you can cool. So those systems will practically be losing entropy to the environment. There are systems which will gain heat from the environment. So those systems will be gaining entropy. So it is not necessary for a system which is not isolated. Increase or decrease is not necessary. It can go either way. But for an isolated system, the entropy always increases. For a system which is not isolated, the entropy can increase or decrease both. Okay. All right. So the answer to this question is option 2. I'll call it option B, increases and maximum. Okay, that's question 1. Let's go to the next one. Which of the following statements is true? A given macrostate typically corresponds to a huge number of microstates. A given macrostate always has exactly one microstate. Entropy is a function of the microstates of the system, and different microstates always correspond to different macrostates. So tell me which of the following statements are true. Firstly, maybe let's talk about this. What is a microstate? What is a macrostate? What's a microstate? So, for example, you have a system of gas molecules. Okay, so basically there is a container which contains, say, neon gas, some gas. So, what is a microstate exactly? One microstate corresponds to one particular snapshot of this system. Okay, so in this system, there will be, say, lots of 10 raised to power 23 order of atoms inside of it, right? Each atom is going to be at a particular position and at a particular velocity. Each atom will have a particular position and a particular velocity. So you take a snapshot of this system at any one instant. So every atom there will have some position, some velocity. That is one microstate of this system. Another snapshot, maybe say after some 10 seconds, you take another snapshot of this system. So that will correspond to another microstate where the position of all the atoms might have changed. The velocity of all the atoms might have changed because of collisions and stuff. So this new state now, where all the atoms are at some different positions, all the atoms have some different velocities, is the new microstate. So this is something called microstate. What is the macrostate corresponding to this? Macrostate, as in these are basically the quantities that you can measure. Macrostate is defined by the quantities that you can measure. For a gas, it can be pressure, velocity, temperature. So a gas at a given pressure, given velocity, sorry, not velocity, volume. So gas at a given pressure, given volume, and given temperature. That's one macrostate of the gas. Is that clear? So I say that this particular gas is at say 10 atmosphere pressure. It has say 2 liters of volume and a 300 Kelvin temperature. So this is one macro state of that gas. Inside of this macro state, your atomic arrangements can be innumerable. Your atoms can be arranged in many different positions. It can have many different velocities. So that is why one given macro state can have a huge number of microstates. Does that make sense? I'm giving the example of gas, but you can think of other examples as well, of course. Any other kind of system that you have, the macrostates and microstates will be accordingly different. So, for example, the staircase example that we had, that is in the lectures, right? So, every individual arrangement of people on the staircase is a microstate. The total potential energy is a macrostate. So for one particular potential energy, one number of potential energy, the internal arrangement of people can vary. It can be different. So U equal to 10 can have many possible arrangements of people. Each arrangement of people is one microstate. So U equal to 10 can have many number of microstates, right? Similarly, that's why we're concluding that one given macrostate typically corresponds to a huge number of microstates. So option A is definitely correct. A given macrostate always has one microstate. This is definitely wrong. Entropy is a function of the microstates of the system. Is this correct or wrong? Guys, someone respond. Kirtika. Kirtika, tell me, is the third option correct or not? Kirtika, please unmute yourself and tell me whether option number three is correct or not. It's okay if you give wrong answers. There is no need to give correct answers only. We are discussing here. We are trying to learn. So just unmute and tell me whether option number three is correct or not. Okay, anyone else who can say this? Anyone else who can give me an answer to this question? Is the third option correct? Entropy is a function of the microstates of the system. Is this option correct or wrong? Okay, wrong. Okay. What is entropy? Entropy is given by minus k ln omega. What is omega? Omega corresponds to the number of microstates of the system. Right. Omega corresponds to the number of microstates of the system. We take a log of the microstates and multiply by this Boltzmann constant k, and you get the entropy of the system. So clearly, entropy is a function of the microstates of the system. Actually, that's the most interesting part about entropy. All other macrostate properties that we talk about, uh, which is say internal energy, pressure, volume, temperature. This one particular quantity is something that connects both macro and microstates. There is no direct connection between microstates and internal energy or microstates and temperature. There is no direct connection. Entropy is that connection between microstates and some measurable physical quantity, which is entropy itself. Entropy gives you that connection between the microstates and macrostates. Derivative of entropy will give you pressure, volume, pressure, temperature, etc. So entropy is that relation between microstates and macrostates. So that's why you have to understand this. What's the significance of entropy as a physical quantity as well? As a physical quantity, it represents something, but as a numerical quantity also, it is very important. It gives you the connection between the atomic world and the macro world that we see. So entropy is a very important quantity, and it actually depends on the microstates. So option number three is also correct. Entropy is a function of the microstates of the system. Different microstates always correspond to different macrostates. This is wrong. they need not always correspond to different macrostates. One microstate can have many microstates. So those many microstates will always correspond to only one microstate. Vice versa, obviously. So option number 4 is wrong. If you have any doubts here, you can ask me. Otherwise, we can move to the next question. Just give me a moment. The recording is on. All right. From standard deck of cards, this is question number 3 now. From a standard deck of cards, if you have a hand of 8 cards, 5 of which are black, calculate the entropy of the system. Does anyone know how to approach this? Does anyone have a idea how to approach this problem? Solve this? Okay. So let me take it. So what they're saying is from a standard deck of cards. From a standard deck, how many cards are there in a standard deck? 52. There are 13 cards, um, 26 cards which are black and 26 cards which are red. In black you have spade and you have what do you call it? Forgot now basically, but there are 26 cards which are black and 26 cards which are red in color, right? So what they're saying is you have a hand of 8 cards. In your hand you have 8 cards out of those 52, and 5 of those cards are black. Okay, so and of course the other 3 are red because they have clearly said that only 5 are black. So calculate the entropy of the system, which means first we need to know what are the possibilities, how many possible hands can you have with this combination, right? So what can you do here? 5 of which are black. 26. Out of those 26 cards, you're choosing 5 cards. 26C5. Um, and multiplied by from the remaining 26, which is why am I doing 26C5? This is for choosing 5 black cards. Choose 5 black cards. And then I'm doing 26C3. This is for choosing 3 remaining red cards. This is the number of possibilities that we have. Um, Now I'll have to use something to solve this. And I have to directly take a log of this. Log of this. Okay, so just give me a moment to get the number here. Combinations I don't know how to in this software. Mhm. Okay, what is this? 26 factorial multiplied by 26 factorial divided by 5 factorial into 21 factorial. Sorry, 3 factorial into 23 factorial. So this is basically 26 into 25 into 24 into 23 into 22 divided by 5 factorial multiplied by 26 into 25 into 20. Okay, let me shift this. Multiplied by 26 to 25 into 24 divided by 3 factorial. This is 5 into 4 into 3, 2. So 5 into 5, 4, 6, 3, 2, 2 and 2 gets cancelled. So basically 3 factorial is basically 6. So this becomes 4. Yes. So why am I doing this is because I don't have access to a scientific calculator right now. So I want to simplify the algebra. So I can just use a basic calculator to do this. 26 into 5 into 23 into 22 multiplied by 26 into 25 into 4 and take a log of this. Okay. Um, okay, so 26 multiplied by 25. Sorry for this, guys. Just a moment. 26 into 25 into 23 into 22 into 26 into 25 into 4. It's a huge number, of course. And ln of this number, ln. That gives me 18.95 as the answer. I get this option as the answer, which is also the correct one. Okay. So what I did was just take a log of this. Um, by the way, here you might be wondering why did I not take minus k, which is the Boltzmann constant, right? So generally what we do is, as in theoretical physics, this is very commonly done, that you ignore the constants and assume the units wherein the constant value would be 1. So basically what you will assume is that this 18.95 is the value of entropy in such units wherein k is equal to 1. So these are very different units. These are not standard, um, like what the standard system you have of units. It's not those that standard system in which 18.95 is the value of the entropy. This is a different unit system in which you are calculating it to be 18.95. But you don't need to get into the hassle of actually putting in the Boltzmann constant and writing it in terms of say minus 10 to the power minus 23. That's we try to avoid that kind of a calculation. So that's why we choose such units so that calculation becomes easier. So yeah, so this value is basically what you get. when you take log of the number of combinations which are present. Okay, number of possibilities or microstates that are present. So that's how you calculate the entropy. Any doubts in this question? Okay. If there are, please ask right away. I'll be waiting for the next question by the time. Yes, please tell me. Question number two itself. Okay, go ahead. Yes. If we are looking at question number three here, I actually calculated the microstates itself, right? Not the macrostates. Hmm. No, that's the point in a way that entropy is a link between. So five is the number of black cards, and what I'm seeing is what are the number of possibilities or uh, number of possibilities basically. Each and every possibility you will be calling it as one microstate, right? What I have to put in. So when you calculate entropy, you are using this expression to calculate entropy. K ln omega. S is equal to K ln omega. Omega is exactly the number of microstates for whatever system you are considering. If you are considering a system which has say five black cards, three red cards, so how many possible microstates does that system have? That is what I'm using to calculate entropy. It's not macrostates, it is actually microstates. Because say total number of cards, here I have already been given that 552 is the total number of cards, 26 of each color. If I had say 104 number of cards, maybe I'm taking two decks. And again, the macro state can still be I have five black cards and three red cards. The macro state can still be the same. But then because I will consider the possibilities, the number of possibilities that I have, and the micro states will increase by a large number. And accordingly, my entropy will also increase. Oh, is it? Can you tell me what lecture is this? Lecture 1 itself. Okay, so maybe I'll get back to you on this. I will have to go through it because this is what my understanding was, which I am talking about. I'll go get back to this. I'll go through it and get back to you in the next one. Is that fine? Yeah, all right. You're welcome. Okay, so any doubts in question number three, how the calculation was done? Okay, so moving on to question number four. Alice has three black and three red cards in hand picked from a standard deck of 52 cards, while Bob has four black and two red cards also from a standard deck of cards. Whose hand of cards has a higher entropy? So there are total number of six cards which are being picked. Total cards six, right? Um, First Alice, three black, three red. What's the uh, what are the number of microstates for Alice? The number of possibilities that we have are again same as previous question 26C3 for choosing three black cards multiplied by 26C3 for choosing three red cards. These are the number of microstates for Alice. Now for Bob, has 4 black and 2 red. So microstates for Bob are 26C4 multiplied by 26C2. We can just simplify it right here. 26 into 25 to 24 divided by 6 multiplied by 26. Same thing. 25 into 24 divided by 6. 3 factorial is 6. So I'm directly writing 6. 26 into 25 into 24 into 23 divided by 4 factorial, which is 6 into 4, 24 multiplied by 26 into 25 divided by 2. This gets cancelled. So the above one for Alice, 26 square into 25 square into 24 into 4. Basically what I did was 4 here uh, and 4 here. Sorry, so 26, 25 into 4 square. My bad. For Bob, the same thing is 26 square into 25 square multiplied by 23 divided by 2. So this portion is the same number of microstates, only this is the difference. This becomes 16 here, while 23 divided by 2 is 11.5. So clearly, number of microstates for Alice is a bigger number, which means because the number of microstates are higher, the entropy for Alice will be higher. Does that make sense? Basically, what I'm doing is I'm calculating the possible microstates and I'm comparing the number of microstates in both cases. And what I conclude is the number of microstates in the case of Alice are more than the number of microstates in the case of Bob. So that is why the entropy for the kind of arrangement that we have in Alice's cards, the entropy is higher for that. That's it. Is that okay? Is that clear? Anyone has any doubts? Oh wait, actually I understood this. Sorry, my bad. The second question, who asked me the question? Who said that Rashi, right? Yeah. Okay, so right, my bad. Entropy is when I'm writing this, entropy is a function of the microstates of the system. Right, the statement is actually wrong, and I understood why. Because it's not actually a function of microstates, it's actually a function of number of microstates. And there is a difference. When I'm saying it's a function of microstates, that means that I change the microstate, entropy should change. But that's not the case. What we are seeing is that it depending on one given macro state, we just calculate the number of possible microstates inside that microstate and talk about entropy. So it is actually a function of macrostate only. You are right, Rashi. So it is my mistake in understanding the question, in understanding the context. Uh, so yes, entropy is not a function of the microstates. It is a function of the number of microstates, and the number of microstates is a function of the macro state. If I give a particular macro state, it will tell me that these are the number of micro states in the given macro state. So actually entropy is a function of the macro states only. So yes, I was wrong in saying that, and the statement number 3 is wrong. Did everyone understand? If not, you can directly stop me and ask the question, just like Rashi did. Please go ahead and directly ask. Feel free to ask questions like that. And thank you, Rashi, for correcting that. All right. Uh, so question number 5. Okay. So question number 5 says, I hope it's big enough for you to see. Okay. Question number 5 says, consider a case where there are three steps in a staircase, all with equal height h, and there are three different people on the staircase with equal weights w. There are three steps basically. So this is 1, this is 2, and this is 3. So step number 1, step number 2, step number 3. 1, 2, 3. And there are three people, different people on the staircase with equal weights. Just a moment. Okay, so consider case there are three steps in a staircase, all with equal height h, and there are three different people on the staircase with equal weights. Okay, so what we want is the potential. What is the potential energy if someone is standing on this staircase, on staircase number 3? If someone's standing here, what's the potential energy? I'm actually confused with the arrangement that generally happens. Um, okay, maybe I'll initially begin with the assumption that this is also at some height h. Step number one is also at some height h. So anyone who's on this step, on step number 1, the potential energy is WH, because weight into the height, we are again in the units where gravitational constant we are ignoring. So weight into height, h into W is the potential energy. On this step, it's 2WH, and on this step, it's 3WH. How many release can the potential energy be? 8WH. Okay. Um, right. So what can we do here? We want the potential energy to be 8WH. How can we do this? The first step is WH, second is 2WH, 3WH. We have only three people to place. So the only thing that seems possible here is that two people go on step number 3. So 3WH into 2, because two people on that step, and one person on this step, plus 1 plus 2WH into 1. One person on this step. So that gives me 8WH. So this is the only possibility that is feasible here. There is no other possibility. So now in this case, because all the people are different, so what do we do is from the three people, we'll choose one person who goes on step number two. So 3C1, and the rest two people will go on step number three. So that is just one. So 3C1 multiplied by 1. So the total number of possibilities are 3. Is this clear? Is this clear to everyone? What? How many ways can the potential energy be AWH? Only three ways. Okay, if you have any doubts, do ask me. I'm moving on to the next question. Yes. For the same system as the above question, what value of the potential energy will have the maximum possible ways of occurrence? So again, you have WH, 2WH, and 3WH. So you have just three people, and you have to place them here. Here I can't think of a directly optimal way to solve this without going through the options. Like, okay, so let's do this. What are the possible combinations that we can have? Everyone on this step number one. So all three people on step number one. This is 3WH. That is the first possibility. Actually, possibilities are many then in that case. Um, say if I say 2 on WH plus 1 on 2WH, then it becomes 4WH. 2 on WH plus 1 on 3WH becomes 5WH. Actually, let me take this out first. No, we can work through the possibilities. I think we can. This is a small problem. Uh, 3 into 2WH is equal to 6WH. 3 into 3WH is equal to 9WH. So what I'm doing is I'm just listing all the possible energies that these combinations can have. So first possibility I'm saying is that all three people are on the staircase WH. I mean the first staircase. So the total potential energy will become 3WH. Then I'm saying the next possibility is everyone is on the second staircase. So that is 3 into 2WH, which gives me 6WH. Then I'm saying all three people on the third one. So that gives me 9WH. Now I'll start considering other possibilities, wherein say there will be two on the staircase one, one in staircase two, two in staircase one in staircase three, two in staircase two, etc. Vice versa. All possible combinations. This is a very like actually literally counting. I'm doing is I'm literally counting all the possibilities. So it becomes very hard if it's a bigger system. But for a smaller system, you can do this. You can literally count all the possibilities. And generally, the maximum number lies between the average of uh, the maximum and minimum energy. So the maximum energy is 9WH. My 9WH is the maximum potential energy. A minimum is 3WH. So 9 plus 3 by 2 is 12 by 2. So 6WH, close to 6WH will generally be the highest number of possibilities. But let's check this. So I said 2 in step 1, 1 in step 2, 2 in step 1, 1 in step 3. That is 4WH, 5WH. Now let's change 2 in step 2 and 1 in step 1. This gives 5WH again. 2 in step 2 plus 1 in step 3. 4 plus 3, 7WH. Now 2 in step 3 plus 1 in step 1, 7WH. 2 in step 3 plus 1 in step 2, 6 plus 2, 8, 8WH. And one more. Acha, wait. Now I'll have 1 on each step. 1 in this step plus 1 into this step plus 1 into this step. That gives me 6. That gives me 6WH. So it starts from 3WH. 3WH has the minimum just one possibility. 4WH also has this one possibility. 5WH has two. When we go close to 6WH, you will have the number of possibilities increasing. 5WH has two, 6WH also has two, 7WH also has two. This and this. I actually should write in different colors so that it's clearer. Okay, so 3WH is just one, 4WH is also one, 5WH is, I'm writing in blue color, here and here. 6WH is here and here. 7WH is here and here. Two possibilities each. 8WH also is one possibility, 9WH is one possibility. So the graph kind of is something like this. You start with one possibility, 3WH, 4WH, then 5WH, 6WH, 7WH. Then again you fall back to 8WH, 9WH. This is 3WH, 4, 5, 6, 7, 8, 9. I hope this is clear to everyone. Uh, I think I have covered all the possibilities from what I understand. If at all I've missed something, you can tell me. Two here and one here. What? Yes, is someone saying something? I think by doing this, I've covered all the possibilities. And I think this is the graph that you eventually get. So among the options, the maximum possible ways of occurrence happen for 6WH. So this has to be the answer. Okay. Okay. So how much difference does that make? Here in this case, I can have 1% everywhere, and this will be 3 factorial possible ways. Is it? Yes. This will be multiplied by 3 factorial. What about this one? 3 into 2 WH. So this is just one. What about the others? Say for 5 WH, let's see. 2 into WH plus 1 into 3 WH. Um, so I'll choose one person, 3C1. So this is, yeah, this is into 3. And this is also into 3. Because this is also 3C1 only. So 5 WH has total number of 6 possibilities. 6, yeah, 6 possible ways. This has also into 3, into 3. This also has 7 WH also has 6 ways. And 6 WH has 6 plus 1, 7 ways of occurring. So yes, in that way, 6 WH has the maximum possible ways of occurrence. This was a very weird way of explaining. Let me explain this again. Um, so what I did was, firstly, I noted all the possibilities of energy and what arrangement gives me that energy. Okay. So, so what I said, as previously I mentioned, 3 into WH, which is I'm placing all three people in the in staircase number one. That is one arrangement, one possible arrangement of people. I'm placing all people in staircase number two. I'm placing all people in staircase number three. These are three different arrangements I talk about here. And what are the possible occurrences in this case? As in, can I arrange the people with differently with this energy levels? So no. Here, if I'm putting three people all in one staircase, then there are no different arrangements. It's just one way. I just put all the three people in one staircase. That's the only way to arrange this. So each of these possibilities is just into one, into one, into one. Next, we think of other possible arrangements. So I can have two people on stair number one, one person on stair number two. How many different combinations are possible here? So I'll choose one person from the three people and put that person on stair number two and the other two on stair number one. So this has three possible arrangements. The arrangements, like number of arrangements, which will give me the energy 4 WH through this kind of setting is just three. Person number one will be on staircase two, and two other people will be in staircase one. Person number two will be in staircase two, two other people will be in staircase one. Person number three is in staircase two, two other people in staircase one. All these three possibilities will give me 4 WH energy. So that's why 4 WH into 3. Similarly, 5 WH also, two people on staircase 1, one person on staircase 3. That also has three arrangements possible. This second way, in which two people are on staircase 2, one person is on staircase 1, this also has three arrangements. All of these have similarly three arrangements possible, into 3, into 3. This one has this one has more number of arrangements. This has 3 factorial ways of arranging. The final arrangement I'm talking about is one person on staircase 1, one on staircase 2, one on staircase 3. Right? So how many arrangements are possible in this particular thing? It is 3 factorial. I can shuffle any person anywhere. So this one has 3 factorial arrangements possible. So that's why this 6 WH has 3 factorial arrangements. I hope this is clear. So now once this is clear, what we are asking is the maximum possible occurrence of a particular potential energy. So 5 WH has 3 plus 3, which is 6. 7 WH has 3 plus 3, which is 6 again. But 6 WH has 3 factorial, which is 6 plus 1 here, which is 7. So that's why 6 WH is the answer. It has the maximum possible occurrences. Is that fine? If there is any doubt, please go ahead and ask a question directly. I'll move on otherwise. So here basically the only difference is from what I did was previously I did not consider them to be different people. I considered them to be the same person, and that is where the problem lies. If I if you consider them to be the same person, this is the graph that you get. By the way, is my screen changing? Is my screen visible? Someone will have to answer this. What screen are you guys seeing? My screen is not visible. Yes, someone's raising their hands. Kuna, Kuna Somashekar. Wait, there's some problem here. I'll reshare my screen. Is my screen visible now? Yes. Okay. Okay. So the problem that I solved previously, wherein even though I arrived at the same answer, but the mistake that I made was I did not consider them to be different people. I considered them to be the same, matlab, similar people, which is why I got the same number of possibilities. When I said that two possibilities for 5WH, two possibilities for 6WH, for 7WH. So this graph also that I have, it's consider them to be the similar to be similar kind of objects. Suppose we had similar marbles, which we are supposed to arrange like this, then the answer was correct. But when you have to consider them to be different people, you also have to consider the possibilities or the permutations within them. Like person number one is in one staircase, person two and three are on some other staircases. So this will give you further combinations within that. So this graph changes, then it becomes, say, 1 here, then directly for 4WH it starts jumping. It jumps to 3. 5WH it becomes 6. I have to make it smaller. This is, say, 3, this is a 6, this is 7, this is 7, this is 6 again. At 8WH we have 3 again, and 9WH we have 1 again. So basically I did not draw the graph perfectly, but it is symmetric on both sides like this. And the highest number of occurrences happen at 6WH. So this is what you will get eventually. And this average method generally works. So highest energy is 9, lowest energy is 3. You take an average. Generally your maximum occurrences lie around that average only. Okay. So yeah, that's question number 6 for you. Let's go to let's go to question number 7. Consider a staircase with 3 steps and 3 identical marbles arranged on them. See, now this is the kind of approach, the approach that I used previously is the kind of approach you have to use in this question now. Because here you have 3 steps and 3 identical marbles. So the steps are of height h and marbles are of weight w. How many ways can the potential energy be 6 Wh? And we already have calculated this answer previously. How many ways can the energy be 6 Wh? The answer is, because the marbles are identical, the answer is just two. One weighs one marble on each stair, and another weighs all the three marbles on second stair. This one and this one. So what are the possible arrangements for 6 Wh? 1 into Wh plus 1 into 2 Wh plus 1 into 3 Wh. So basically one marble on each step. That gives me 6 Wh. That's one possibility. The second possibility I'm saying is 0 into Wh plus 3 into 2 Wh plus 0 into 3 Wh. This also gives me 6 Wh. There are no other possibilities for three marbles. Alright, so the answer should be 2. How many ways can the potential energy be 6 Wh? Okay, I'm moving on to the eighth question. Eighth and the final question for this uh, assignment 1 of last year, is that for a system of marbles on an endless staircase, there can be cases of negative temperature. Is this statement true or false? That's your question. For a system of marbles on an endless staircase. So, how do you talk about temperature in this context in simple arrangement of marbles? How do you talk about temperature? You basically draw a graph of this sort. Okay. You draw a graph of this kind, the one I've drawn here, this kind of graph, where there is number of occurrences and the possible potential energy on one axis and occurrence on the other axis. So occurrences basically corresponds to entropy, right? The number of occurrences corresponds to entropy. So basically it's kind of S versus U graph. Not exactly that, but at least the trend is similar. And then what you see is the slope of the graph tells you the value of temperature. Negative of the slope of the graph tells you the value of temperature. All right. Uh, is it negative or positive? Basically, you get the value of temperature from the slope. Is the slope of the graph that gives you the value of temperature. Okay. Now you need negative slope for negative temperature. Yes, it's possible. Plus U is basically T delta S. Delta U is basically T delta S. Therefore, temperature is basically del U by del S. Okay. So us or 1 by T is equal to del S by del U. That's your 1 by T. Negative or positive can simply, negative slope will mean negative temperature. Positive slope will mean positive temperature of the S versus U graph, right? S versus U graph, negative slope corresponds to negative temperature. Positive slope corresponds to positive temperature. Okay, so now you have a system of marbles on an endless staircase. Okay, so the staircase keeps on going, dot 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 dot, and what you have to draw is again U versus S. What kind of slope do you expect to have here? S is basically number of occurrences. So let's think about occurrences only. When the staircase is endless, you keep on increasing uh, potential energy. Say, for example, you start with 3 WH. So there is everything is here itself. All the marbles are on the first staircase itself. This is step number 1, 2, 3, 4, etc. The potential energy is WH, 2 WH, etc. So when I say I start with 3 WH, value of U, your in the number of occurrences is minimal because all three here. Then when I increase the energy to say 6 WH, then the possibilities increase because it can be all three marbles here, one marble here, all three marbles on step number 2, one marble on step 3, one on step 2, one on step 1. Even that's an arrangement. Uh, there can be many other possibilities. Actually, it's identical marbles, only two possibilities. Sorry, for 6 WH there will be only two possibilities. Then you increase the energies to say 20 WH, for example. You can also have something like 20 WH. So then the possibilities is like 1 on 19, 1 on 1. Sorry, 1 on 18, 2 on 1. 1 on 17 or 16 and 2 on 2. Do you get what I'm trying to say? As you keep on increasing energy, your possibilities, because there are infinite number of stairs. So you can have many different possibilities which will total to give you 20 WH. If I have 40 WH, then the possibilities increase, which can give you 40 WH, because I can use all the previous steps from 0 to 40. I can use to arrange those three marbles. If my total potential energy is 80 WH, I can use all the 80 steps in the below 80 WH. I can use all the steps and arrange those three marbles to give me 80 WH. So that is why the number of occurrences keeps on increasing as you keep on increasing the potential energy. So in this case, I'm not drawing the exact trend here, but what I'm trying to show is you will always have positive slope because the number of occurrences keep on increasing. That is why, because you never have a negative slope, you never have negative temperature in this. You always have positive temperature. So that's why for a system of marbles on an endless staircase, there can be cases of negative temperature. This is false. Yes, so we have been through entire assignment number 1. Hopefully the questions in your assignment are also going to be similar. So you should be able to solve it. If you have any doubts in this assignment, please ask them right away, or else we can end the session and meet next week. Are there any questions? Okay, then I assume there are no questions. Then thank you for attending, and let's meet next week. Bring your doubts and use the forum. Again, I'll reiterate, please use the forum to ask any doubts that you have when you watch the lectures. Even if you have doubts in some problem, some question, try to explain the approach. After, okay, you can explain the approach and try to ask the question. Don't ask how to solve this question. I'm talking specifically about numerical questions only. About derivation or any other kind of doubt that you have within the lecture, that also you can post. You can post whatever kind of doubt you have on the forum. All right. So use the forum, question forum, and you can also use the live session to ask your questions. So, all right, let's meet next week and thank you.